Hello, this is Group 6, and here's our presentation on masked ORB-SLAM3. We're going to go over what inspired us, our approach, the experiment setup, our results, and a summary. What inspired us is a system called DynaSLAM, which attempts to remove dynamic objects from the scene in order to increase SLAM accuracy. However, this led to more questions. In an autonomous driving scenario, would dynamic element exclusion using ground truth segmentation masks increase localization accuracy? If so, then would predicting segmentation masks do this as well? The first component in our architecture is a mask RCNN. We manually identified dynamic object classes in the COCO dataset, and then used the mask RCNN pre-trained on this dataset for instance segmentation to segment these dynamic elements. The other component of our architecture was SLAM. We chose to expand upon an existing implementation called ORB-SLAM3. Our goal is to have ORB-SLAM3 operate normally in a dynamic element-free environment. It is worth noting that pre-processing our data is not sufficient. ORB-SLAM3 uses features generated in the tracking phase to perform localization. Thus, we propagate our masks into the feature module of the implementation. The location of our features is described as 2D real-numbered coordinates. For wider coverage and indexing purposes, we interpolate these features to the 4 surrounding integer coordinates. Then, by utilizing our masks, we check for features that are overlapping with dynamic elements. These features are then discarded, and the rest are preserved. The SLAM implementation then continues as normal, and this happens for every frame. To test our approach, we perform 2 experiments. The first experiment compares our masked ORB-SLAM using ground truth masks with the original ORB-SLAM implementation. To acquire ground truth masks, we use the MOTS dataset, which is a subset of the overall KITTI dataset. Unfortunately, this dataset did not contain the ground truth trajectory, thus the raw GPS data was selected for comparison. In the second experiment, we use KITTI data from the odometry subset, which does contain ground truth trajectory, but does not contain ground truth masks. In this scenario, we utilize our mask RCNN to compare our masked implementation to the original ORB-SLAM implementation. Here is a quick demo video. Here are our results for experiment 1. As you can see, there are features on the dynamic objects in the top left image, which is the original ORB-SLAM approach, but in the bottom image, after the mask is applied, the features are no longer there. We can see that the ground truth version performs similarly to the original one, but we can't discern which one performs better due to the GPS data not being sufficient. However, in experiment 2, where we use our mask RCNN and have access to ground truth trajectory data, we are able to see that our approach does perform better than the original ORB-SLAM. The left graphs show position, while the right graphs show angle. When comparing average pose error, we can see that our method halves the error from the original implementation. Here's another error visualization over time. Lastly, when we consider error density, we can see that we removed most of the long-tailed error in favor of smaller error. So let's revisit our hypotheses. For the first question, in an autonomous driving scenario, would dynamic element exclusion using ground truth segmentation masks increase localization accuracy? Since ground truth semantic labels and ground truth trajectory data were both not available at the same time, we can only attest to the results being very similar between the masked approach and the original approach. Both follow the same trend when compared to the raw GPS data. As for the second question, do our predicted masks increase localization accuracy? Yes, our mask RCNN segmentation mask approach increased localization accuracy. Since the predicted segmentation masks are more inaccurate than ground truth labels, this also likely suggests that the ground truth labels would have been even more accurate. To summarize, in an autonomous driving scenario, we propose utilizing this method of removing dynamic elements from scenes in the context of solving the SLAM problem. Our results show that through using a mask RCNN and modifying ORB-SLAM3, we're able to increase localization accuracy over the original ORB-SLAM3. For our future work, if new data with ground truth for both trajectory and semantic labels becomes available, we can further validate our results. We also would like to attempt this methodology in a LiDAR-based SLAM approach as well.